What is the outcome of DBA with acetonitrile? This is acetonitrile and this is DBA. This is our other way of writing DBA. Notice the al gives you a hint as to the product. Even though that stands for aluminum, it can remind you that it makes the aldehyde. What is the outcome of gamma-butyrolactone with DBA? Again, there's your hint. It's going to make the aldehyde, but notice the chain gets cleaved. This part leaves as a leaving group, and it's got to stay. So notice 1, 2, 3, 4 carbons, 1, 2, 3, 4, and on the end you've got that alcohol. So how would you prepare N-ethyl hexanamine from acetic acid? Well, here's the acetic acid, and here's N-ethyl hexanamine. The way that I like to do this is I like to look at carbons and try to figure out where in the molecule they could be related. So I see these two carbons, so I look for two carbons here. It could be these two carbons, or it could be those two carbons. It can't be at the very end down here, or unlikely. If those two carbons from the acetic acid were these, how would I get these other 4 carbons on there? It's kind of hard. So let's start thinking it through, putting these 2 carbons here. Well, how could that have been? Well, I think 2 carbons, acid. Well, let's see if we can get an acid derivative and make this. Well, how can I get this? Well, that could come from an acid chloride and the amine. Okay, how can I do that? Well, I could take this acetic acid and make it into the acid chloride. So let's go ahead and now put in the reagents that we need. To go from the amide to the amine, I need lithium aluminum hydride. To go from the acid chloride and amine to this amide, I just need to mix them together with either excess amine, or you could put a little pyridine in there to catch the hydrochloric acid that would be formed. And then to make the acid chloride, so how would you make 4-decanone from 1 chloropropane? Well, here's the 1-chloropropane, and here's the decanone. How are you going to make 4-decanone from this? Well, let's match up carbons again. Where could these 3 carbons be? The only thing that really seems to make sense to me is for them to be right there. It's just, that's too long a chain for those 3 carbons to be in there. Could they be here, these 3 carbons right there? Or these 3 carbons? I just don't see an easy way, but I see an easy way to take these 3 carbons from here. How? Well, I can add another carbon by making the nitrile. Once I make the nitrile, I can convert this to the acid chloride, acid and then the acid chloride, and then couple it with a Gilman reagent. So now these are the reagents that I'm going to need in order to do an SN2 on this chloride and replace the chloride with a cyanide. Then what do I need to do? Hydrolyze the nitrile to an acid functional group and then treat with thionyl chloride. Once I have thionyl chloride, I treat that with this Gilman reagent and I end up making that ketone. Don't forget that we do have spectroscopy. The carbonyl wave number can help us identify the type of carbonyl. Notice that the except for the amides, the reactivity of these, actually it really is an order of reactivity because amides are less reactive than aldehydes and ketones. So if I look at acid, chlorides, anhydride, esters, and then down to amides, it's all going in order of reactivity from higher wave number down to lower wave number, and then you have the ketones in there in the low end. The NMR chemical shifts are about the same for all of the carbonyls, The only one that really is different is the aldehydes have that hydrogen attached to the carbonyl that's way down there at 10 parts per million. But the rest of the NMR chemical shifts would be for the the hydrogens that are alpha to the carbonyl, and they all are at about the same place. And then the other thing that you have with mass spec is you still have alpha cleavage in the McLafferty rearrangement available for all of these functional groups. So you go ahead and look at this spectrum and assign which peak belongs to which hydrogen in ethyl acetate. Well, here is ethyl acetate. Let's go ahead and assign the protons. These protons are alpha to the carbonyl. Where are they going to be located? They're going to be right here at about 2. These hydrogens are on the carbon that are attached to an oxygen. That's a pretty electron withdrawing situation. So where are these? Right there. And that quartet helps tell you that. This is a singlet that helps tells you that that's those hydrogens. And then where are these hydrogens? Well, they're that triplet way down there, upfield in the spectrum. There are other esters, particularly esters that you see in biochemistry. You see phosphate esters, the ADP, ATP, they're phosphate esters. You see thioesters. Coenzyme A is a thioester, and you see that participate in a lot of biochemical reactions. So realize they behave very similarly to all these acid derivatives that we've been looking at. And when they do a lot of their reactions, you'll see that they do nucleophilic attack, forming a tetrahedral intermediate in between. There are polymers that are acid derivatives. For instance, look at this polyester here. This is the structure of a polyester, one type of polyester. This is the ester functional group. Notice this came from a diol. That part was 2 alcohols, a diol on either end. And then see this part? This came from a diacid. So what you do is you take these and condense them down, or you can change the diacid into a diacid chloride and react them with a diol. There's a lot of different ways to make polyesters. You can make polyamides. Notice this is a diamine, and this is a diacid. So you just do a regular amide reaction like we've done in the previous slides. So what polymer would you form from this dimethyl terephthalate and ethylene glycol? Notice this is at 200 degrees. And what you're actually going to do is drive off methanol as a byproduct. This is what you would form as a polyester. See, this is driven off as an alcohol because the heat's so high. As soon as it forms, this is going to do nucleophilic attack. And even though the methanol isn't a great leaving group, once it does leave, it's going to pick up a proton and be boiled off immediately at such a high temperature. So we end up making this polyester. Here is these 2 carbons, and here is the terephthalate part, and you just get this big long chain of these in a row. What polymer would form from adipic acid and hexamethylene diamine? Well, what we're going to do here is we're going to actually, what we actually usually do is form the adipoyl chloride and mix it with ethylene diamine and do it at room temperature. But you can actually do this polymer by mixing them together and heating them. And what do we get? Here is the diacid, and here is the diamine, and you make a big long polymer. This is a polyamide. So what is the product of the Grignard reaction of an excess of phenylmagnesium bromide with dimethyl carbonate? Well, this is dimethyl carbonate, and this is the phenylmagnesium bromide, and we're going to have excess of it. Why? Well, because we have an ester functional group here, and the alcohol portion will leave to allow another attack of the Grignard reagent. What will happen is we'll get 3 substitutions here. 1 for the elimination of this alcohol portion, 1 for the elimination of this alcohol portion, and then another for addition to the carbonyl. So we get this triphenyl methanol product after acid wash, of course, which is not shown. What is the IUPAC name for this compound? Well, let's go ahead and look at these. This is the acid side, and it's an amide, so we're going to call it a propanamide. And you can see there's only one propanamide here. You wouldn't say propane amide. You wouldn't say all these others, so we're going to say propanamide. And then we look at this and we say, well, how do we name this? We name that as an alkyl group. What is it? 1, 2, 3, 4 butyl group. And it's on the N, so N, and then it's butyl, but on the number 2 carbon you have a methyl. So N parentheses 2 methylbutyl propanamide. This is the correct name. What is the IUPAC name for this compound? Well, this is an ester, so we look at the acid side first. 1, 2, 3, 4, 5. That's going to be pentanoate. But we've got some methyl groups on there. So this is going to be 3,4 dimethyl pentanoate. Well, we've got this phenyl. Where is it going to be going? Well, that's a separate chain, the alcohol side, so it's got to go in front. So we're going to say phenyl 3,4 dimethyl pentanoate. Remember, benzyl has an extra methylene group in there. We would not say benzyl. So this is the correct answer. What is the IUPAC name of this compound? Well, the longest chain that we have that has a functional group is this. So this is 1, 2, 3, 4, 5. That is pentanoyl bromide. Where's the phenyl? 1, 2, 3 phenyl. You would not want to call it propanoyl because that's not finding the longest chain. So it is going to be 3-phenyl pentanoyl bromide. Which of the following statements is true regarding these 2 carboxylic acid derivatives? Well, let's look at statement A. Only molecule A can be hydrolyzed. No, we know all acid derivatives can be hydrolyzed. Only molecule B can be hydrolyzed. Of course, no. Both can be hydrolyzed, but A will react faster than B. Amides are more resistant to hydrolysis than esters, so no, that is not true. Both molecules can be hydrolyzed, but B will react faster than A. Well, that is true. A and B can be hydrolyzed at roughly the same rate. Well, the ester is going to be slightly faster than the amide. So this is correct. Predict the outcome of the following reaction. Well, an acid with thionyl chloride is going to give us the acid chloride. So that is the correct answer.